Right, so in this chapter, chapter 8, we will actually see an application of those linear algebraic equation. Where do they come from, and solving them, why would it be useful for us? All right. So one important application is this eigenvalue problem. So this is a class of problem which is very relevant to mechanical engineering. And when people eventually come up with, they start the problem and write the forces and reduce their system to an eigenvalue problem, it's considered as if we are done. Basically, people say, well, we are done. Here's an eigenvalue problem. You can just send it to MATLAB and get the eigenvalue. Right? So this is like the mess, really, for engineering. You know, it's as if, yeah, just integrate this and get the solution. You're done. Just integrate this differential equation. So also, when you reduce the problem to an eigenvalue problem, you are done. You send the matrix to MATLAB or Scilab or whatever and tell him, give me the eigenvalue. So we'll see where this comes from and how we can actually solve it ourselves, how we can get the eigenvalue. So what is the eigenvalue problem? The eigenvalue problem, basically, it's for a matrix to get its eigenvalue, it's to get this lambda. What's that? This is A multiplied by X equal to lambda multiplied by X. So a matrix A, you know, 1, 2, and minus 2, and 3. This matrix multiplied by x1 and x2 will be equal to lambda, that's a number, multiplied by x1, same x1 and x2. So the effect of the matrix on the vector is the same as a scalar, lambda, on the vector. Same effect. So multiplying A by X will give you exactly the same result as multiplying lambda by X. So that lambda is called the eigenvalue of that matrix. So I will show you how did this come in actually mechanical engineering system, right? And why getting lambda is really important for us, right? What's the question?
Will this be posted on the website, the D2L?
Right, the lecture is already posted there.
Oh, okay.
And you should have printed it before you come to class so that you would write your notes on my notes rather than starting from scratch. It will be easier. So my recommendation is that and I really try very hard to post it at least one day before the class so that you would have the time to print it. Okay? Because it's one thing to just have the notes posted after the lecture. It's another to actually write on the notes in the lecture. That would be even better, you know, while you're still fresh and listening. So I would recommend that you print them. Okay. So this lambda is called the eigenvalue, and that vector that will do that trick also, that multiplying the matrix by that vector will result in the same number as multiplying lambda by that vector. It's called the eigenvector. So every eigenvalue will have an eigenvector. And the homework to this week is basically about this. It'll give you a matrix and tell you calculate the eigenvalue and calculate the corresponding eigenvector. Right? So again, of course, x equals 0, that's the trivial solution. We are not interested in because if x vector is 0, that's eigenvector for anything. Right? No, we are not interested in this guy. So to start with, what is this? The meaning of this lambda is that, so here is a vector 5 and 1, for example. Okay, 5 and 1. So this is on x1 and x2 coordinate system. 5x1, 1x2. So multiplying this matrix 6 and 3, 4 and 7 by 5 and 1 will result in 33 and 27. That's this vector. This vector is completely different direction, completely different vector than the original one. But look at this combination. This same matrix A, if you multiply it by this vector, 3 and 4, not 5 and 1, will result in, and you can check on us, right? Will result in 30 and 40. So here is the original 3 and 4, and here is the original 30 and 40. So multiplying this matrix by that vector, it's as if you multiplied 10 by the same vector. It's as if basically you just stretched the vector or shrinked the vector by a factor of 10 or factor of. So the matrix, basically multiplying it by that vector, didn't change the direction of the vector. Okay, so geometrically that's what happens. Okay, so again this is the eigenvector, and this factor is called the eigenvalue. Right? So in short, this is a problem we are solving. For any matrix A, what is that vector and what is that value that will do that kind of transformation? Okay, it's actually, when you think about it, it's as if you are turning the matrix into a number. As if you are basically turning the matrix into a scalar that will have the same impact of the matrix, the whole matrix, to that particular vector. Right? So another name, by the way, for the eigenvalue is the characteristic value. We tell you, well, what's the characteristic value for that matrix? All right. So here is the where this is coming from in mechanical engineering. What situation will result in this ax equal lambda x problem for us? This is not just for mechanical engineering, but I mean, let's look at the thing that's relevant to us. So here is a spring mass system. So here is M1 and here is M2 and here is K1 and here is K2. And you guys know that if we basically take those guys to an initial displacement, so by initial displacement we take them to a certain place, or we apply a force on them, someone pushed on them, what will happen? They will start oscillating, right? And if there is no damping in the system, they probably will just keep oscillating forever. But if you have damping, then eventually damping will even kill that vibration until they stop. And so in order to basically find the response of the system to the displacement, initial displacement of initial force, we have to write the differential equation that control this system, right? And solve it to find y as function of time, so that we can basically be able to find out y as function of any moment. Okay, so how do you write the differential equation that control this thing? Well, what's the physics of this motion? What controlled the motion of the spring mass system? What is that guy? Summation of the force equal m time acceleration. So if y is the displacement, y dot is the velocity, y double dot is the acceleration. Why use y dot? Y dot is dy by dt. That's why it's the velocity. And y double dot, that's basically dy dot by dt. So it's the differentiation of the velocity. Okay. So what do you call this? The forces is equal to mass time acceleration. I can't hear. Newton's second law, right? The force is equal to the mass times acceleration. So you write this for the mass 1 and you write this for the mass 2, and you will probably end up with two equations for the two masses. And those two equations will be differential equation, right? Because you have d2y by dt, right? This is actually d2y by dt, or d2y by dt squared, the second derivative of the y. So this will end up being differential equation in y1 and y2 when we write for the second mass. That's not algebraic equation. What are you talking about? Where is the... Well, I'll show you how the differential equation will end up yielding algebraic equation, and those two algebraic equation will be an eigenvalue problem. Will be exactly a time y equal to lambda time some y, right? And our job would basically to find the lambda and find the y, because we want to solve the system. We want to find out where it will move. Alright? So to write the differential equation, the Newton's second law for the first mass, I need, what do you call this? The free body diagram. You put the forces acting on it so that you would say, well, here is the mass times acceleration equal the forces. So I start by, well, here is m1, here's the direction of not just y1 double dot, it's also y1 dot, this is the plus direction of y1 dot, and also y1. Okay? And I choose to make this the plus direction. And same thing for m2. So here is the plus direction, and so this is the plus direction for y dot 2 and y2. And we write the forces on them. So what are the forces? Forget about gravity. Okay, let's neglect gravity in this one. So the forces are mainly or only the tension in the spring. Alright? So if we take this guy y1 down and this guy y2 down, and by the way, they don't have to start with only plus y1 and plus y2. I mean, you can start the whole thing by pushing the guy up and pulling this one down, or the opposite. He still will vibrate, but depending on the different initial displacement, the motion will be different, right? So, but you just assume that it's the y1, it's basically in this direction, and y2 in that direction. And then if it's actually initially it's -3, that's fine. You put it in the system as at t equals 0, y1 was -3. Alright? So you'll also have to assume which one is bigger. So let's assume y2 is bigger than y1. So basically that creates tension in this spring, right? Because if y2 was smaller than y1, that means that the first spring, the top spring, is under tension, but the second one is under compression, right? So assuming y2 is bigger than y1, well, this guy will be under tension. How much? So the force in a spring is k delta y. That's the spring constant, and delta y, that's the displacement on the spring, right? The tension spring. So y2 minus 1, if you take this guy 7 centimeter and this is 1 centimeter, then that spring is under 6 centimeter tension, right? So he will have a force on this mass trying to pull it up, k2 y2 minus y1. Of course, on the other mass, he will try to bring it down, right? So he's pulling this guy up while he's pulling this guy down. So that's why in this mass you'll find k2 y2 minus 1 is actually pulling it down. And don't forget that the first spring is also under tension. We're assuming that we start with y1. So you have k1 y1 because this other side is wall. So the only displacement is y1. So here is the free body diagram for the mass 1. Here is the free body diagram for mass 2. And here is simply the Newton's second law. Mass times acceleration, m1 y1 double dot. So I don't want you to get confused if you see this, or you see this, or you see this. They are all basically telling you it's the second derivative of y1 with respect to time. Alright? They are all the same. The two should like this. Alright, so mass 1 times acceleration 1 equal to the forces, and the forces are considered plus if they are moving in that direction. So that's why, so by the way, k1 has a value. So this k1 y1, this should be minus because this is the plus direction. So because it's pointing up, it's minus k1 y1. k1 is 3. That's the spring constant for spring 1. So minus 3 y1, and this guy should be plus. It should be plus k2 y2 minus 1 should be plus k2, which is 2. Should be plus 2. But see what he did? He's make it minus 2 y1 minus y2 rather than y2 minus y1. Same thing. And the same thing for the second mass. Mass times acceleration m2 times its acceleration equal to the forces, and the forces are plus if they are pointing in that direction, minus if they are pointing up. So minus k2 y2 minus 1 minus k2 y2 minus y1. Let's finish the numbers together, and so you will end up with, and by the way, m1 and m2 are just numbers. They could be anything, 5 and 3, 2 and 1. It turned out to be in this problem 1 and 1. So 1 and 1. So here is y1 double dot equal to minus 5y1 plus 2y2. y2 double dot equal to 2y1 minus y double 2. This is two simultaneous ordinary differential equations. And we will learn how to solve them later as differential equation in the course. But for now, actually the problem reduced to an eigenvalue problem, which again, as I told you, it's really actually easy to solve using just eigenvalue techniques. Right? So how we turn this differential equation into algebraic equation? How are we going to do this? So first of all, this is just copying it from here to here. So the y double dot is basically this matrix time y, right? This matrix, which is the minus 5, 2, 2 minus 2. So the y double dot, which is basically those two guys, is basically equal to this. Alright? So now the solution, the shape of the y, remember we're solving it basically is to getting y1 as function of t and y2 function of t. That's what solving an ordinary differential equation will give you. What is y1 and y2 is doing with time? Are they going to oscillate like this or going to oscillate like this? Or? So one technique to solve this is basically to say, I don't know the exact number, I don't know it's 5 or 7, but I know that it's going to be a constant a1 times, say, a sine t, and a constant 2 multiplied by sine t. You know the shape of the function. That could help. Then if you do this, you plug that solution or that shape of the solution in the equation and you get those constants. That requires prior knowledge. That requires that you actually know the solution. So we know from our experience in spring mass system that if you bring those spring down, or this mass, if you pull them down and you leave them, what will happen? They will fluctuate. We know that they will not just shoot and hit the roof and break the, right? We know that they will just keep oscillating. So our physics tell us that we should expect an oscillatory solution. Also the mass tell us something really important. What is the equation? The equation is that y1, if you differentiate y1 twice with respect to time, that's what the second derivative is. This is d2 y1 by dt square. Which is d by dt of dy1 by dt. So you are saying that differentiating y1 twice result in y1 and y2? What is the function that when you differentiate it twice, you result also in the same function, more or less? Definitely, let me tell you, it's not y1 is not t square, right? Why? Because if I differentiate t square with respect to time, I get 2t. If I differentiate one more time, I get 2. So it's not a polynomial. Polynomial doesn't work. It must be something that will give us sinusoidal, or sorry, an oscillatory solution, and you differentiate twice, you get the same function multiplied by a number. It must be in that form. But notice that I only know the form, but I don't know the constant. I don't know the w, I don't know the x. I don't know whether it will oscillate this much or whether it will oscillate this much. I don't know whether it will oscillate like this or tick, 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 tick. So I don't know the magnitude or the, so I didn't really come up with a solution. All I got is the shape of the solution, right? Just based on physics and based on math. Perfect. So we can insert that shape in here and get the constant, the x and w. So this is inserting the solution. So if y is actually x e omega t, then the double derivative, the second derivative of y, would be the first derivative of y dot. And the first derivative of y dot, if you differentiate this with respect to t, this is like e to power at. What's d by dt of e to power at? It's e to power at multiplied by a, right? When you differentiate an exponential, you just get the constant multiplied by the exponential. That's why it's perfect for this solution, because when we differentiate again, we just get a squared multiplied by the same exponential or the same function. That works, huh? So differentiating it twice will result in omega square x e omega t. Why x is not doing anything in differentiation? That's a constant, huh? That's just a constant, like omega is constant. So differentiating it doesn't do anything. So the second derivative is basically based on this. Is going to be omega square x multiplied by the same exponent. So this is basically what will go here. And what will go there is, this is the matrix A multiplied by the y. What is the y? The y is the x omega t multiplied by the a. Alright? So that shape on those two differential equations will result in omega square x e omega t equal to a x e omega t. Again, the e omega t and e omega t are on both sides, so we can actually cancel them. Alright? Why didn't cancel the x2 and end up with omega square equal a? So canceling e omega t will result in omega square x equal ax. My question, why I didn't cancel x and x? Because it's a vector. This is basic. When I say y, this is y1 and y2, and we are saying x1 and x2. Alright? So that's why we didn't cancel. Alright, so we end up with omega square x a equal x. A scalar omega square multiplied by vector x, equal to a multiplied by x. Does this sound familiar? Matrix multiplied by a vector equal to a scalar. I'm not going to call it omega square. I'm going to even lambda. I can call it anything I want. Right? I call it lambda x. It's an eigenvalue problem. And so the guy who's doing the vibration then will tell you, or the system, you tell you, we are done. Here, we know how does it move now. Just send this to MATLAB. He will give you lambda, and he will give you the x. Lambda is omega squared. That's the frequency of the oscillation. When we said that the solution is x e omega t, that's the frequency of the solution. Alright? And you also get the x and the magnitude of each one of them. So the solution, you get the solution of both of them. Alright? So this is what we are trying to solve. And this happened in other systems too, not just in mechanical engineering. Alright?